So we've defined orthogonal vectors, and now I want to think a little bit about orthogonal matrices. So first of all, we need to say that a vector u is a unit vector if the length of u is 0. Sorry, if the length of u is 1. And we've already said that u and v are orthogonal if the inner product is 0. We now say that u and v are orthonormal if they're both of length 1 and if the inner product between them is 0. So let's consider a matrix Q, which is an n by n matrix. We say that Q is an orthogonal matrix if the columns of Q are orthonormal vectors. And if they are orthonormal vectors, you'll hopefully be able to convince yourself fairly easily that that means that Q transpose Q must equal the n by n identity matrix IN. And we'll see in a minute that if that's the case, and if Q is n by n, then this implies that Q transposed is also equal to the identity matrix. So let's prove that. Let's suppose Q transpose Q equals the identity. Then can we show that implies Q transposed is the identity? Well, let's consider the Q as a map. It maps from Rn to Rn, and it takes a vector V to Q V. Now, we know from the rank nullity theorem that the dimension of the kernel of Q plus the dimension of the image of Q must be equal to n. But because Q has a left inverse, Q transpose Q equals identity, we can't have the kernel of Q being anything other than a 0 matrix. So this term must be equal to 0. If you think about it, if the kernel had dimension 1 or bigger, then the dimension of the image of Q must be less than n. And so there's no way that multiplying by Q transposed another n by n matrix can get us back to the identity. We've lost information that we can't recover. So, in other words, the rank of Q must be n. Well, in that case, we know there must be an inverse. Okay? So there must exist a right inverse, B, say, such that QB equals the identity. But if we now multiply both sides by Q transposed, we can see that we get Q transposed QB equals Q transposed. But Q transpose Q is just the identity, so we get B equals Q transposed. Okay, so that's the first bit proven. If Q transpose Q equals the identity, we know that Q transposed must also be the identity. What if Q is n by P, say, with n not equal to P? The question then is, does Q transposed Q equal the identity imply that Q transposed equals the identity? Well, there's a very quick and easy answer to that. The answer must be no. Okay. We know that the trace of Q transposed Q Q transpose Q is IP. So this must be P. But we also know that the trace of A times B is a trace of B times A. So this is a trace of Q transposed. Okay. So that cannot equal the trace of IN, which is N, if N is not equal to P. So to summarise, Q transposed Q equals the identity implies Q transposed is also the identity if Q is square but Q transpose does not equal the identity if Q is not square. So just finally on this topic, let's suppose we are given n vectors q1 up to qn, which are all in Rn, okay, which are mutually orthogonal unit vectors. Then the claim we're going to prove that the sum from I equals 1 to n of qi times qi transposed is the n by n identity matrix. So how will we prove this? Well, first of all, let's let Q be the matrix that has columns given by the QIs. So we're going to put Q1 here. So it's a column vector in the first column of Q. Q2, okay, up to Qn. Okay. Then the fact that these vectors are mutually orthogonal unit vectors, well, that implies that Q transposed Q is the n by n identity. Now, because Q is n by n, Q transposed Q equaling the identity implies that Q transposed equals the identity. Now, what is Q transposed? Well, Q transposed, if we write this out, that's going to be the matrix Q, which has columns, the vectors, lowercase q. Okay, so we've got n by n matrix times Q transposed. So this has rows given by the Qs. So I've in the transposed the column vectors, the lowercase q's, to give row vectors. Okay. So the first row is given by Q1 transposed, the nth row is given by Qn transposed. And we can see that this, we'll think a bit more about this in a later section, but we can see that this is the sum of Qi transposed, the sum from I equals 1 to n. If that's confusing, wait until we get to section 2.4, okay, on matrix products, and we'll spell that out a little bit. Now, each of these terms in here is a rank 1 matrix. Okay. So by doing Q transposed, or Qi transposed, we're forming the matrix capital Q by a sum of rank 1 matrices, just as we did before.